A Chinese lab just claimed its new optical quantum chip runs AI workloads 1,000 times faster than NVIDIA's most advanced GPUs, a claim that spread across tech headlines within days of the announcement. If that number is real and holds up under real-world conditions, it would mean every single AI data center on the planet, every GPU cluster NVIDIA has ever sold, every billion. Dollar investment in accelerated computing just became a rounding error compared to what quantum hardware can theoretically do. That is an enormous claim. So let's actually dig into the proof behind it, look at what serious researchers are finding, and figure out whether your AI chips are actually in trouble, or whether this is another headline running miles ahead of the underlying physics. Let's start with the claim itself, because it deserves a real look before we pick it apart. In November of 2025, a Chinese quantum computing firm unveiled a new optical quantum chip and claimed it could process certain AI workloads roughly 1,000 times faster than NVIDIA's current generation GPUs. The company reportedly has manufacturing capacity for around 12,000 wafers annually, suggesting genuine intent to scale production rather than simply demonstrating a one-off laboratory curiosity. On the surface, that sounds like exactly the kind of civilization-altering breakthrough that should be dominating every technology headline on Earth. Here's the problem. It is the same problem that shows up again and again throughout the history of quantum computing headlines. There remain significant unknowns surrounding this specific chip, including unresolved production yield issues that industry analysts have flagged as a serious practical barrier. A laboratory demonstration showing an impressive speed-up ratio on a narrow, specifically chosen benchmark task is a fundamentally different thing from a chip that can reliably, consistently, affordably replace GPU infrastructure at the scale modern AI companies actually operate at. NVIDIA did not become the backbone of the global AI industry by winning a single benchmark. It became the backbone by delivering consistent, reliable, mass-producible performance across an enormous range of real-world workloads year after year at a scale competitors have struggled to match. 1,000 times faster on paper means very little if the underlying manufacturing process cannot yet reliably produce working chips at any meaningful volume. This pattern, an eye-catching speed-up number attached to serious unresolved practical limitations, shows up constantly in quantum computing coverage, and it is worth understanding the broader context to see why. Google's own headline-grabbing result from October of 2025 offers a genuinely useful comparison point here, precisely because it comes from a Western lab that has been unusually transparent about both the achievement and its limitations. Running an algorithm called quantum echoes on its Willow chip, Google measured something called out-of-time order correlators roughly 13,000 times faster than the best available classical estimate, using just 65 qubits. That is a real, independently verifiable result, reproducible on other quantum hardware of similar quality, and it represents a genuine milestone in quantum computing history. But notice exactly what that result actually measured. A specific physics simulation task, tracking how information scrambles through a quantum system, not general purpose, artificial intelligence computation of the kind running inside ChatGPT, image generators, or the recommendation algorithm behind your favorite streaming app. Quantum computing researchers have been explicit about this distinction, and it is a distinction that tends to get flattened or lost entirely once the impressive-sounding speed-up number escapes into more sensationalized tech coverage. The honest technical community covering this field consistently notes that these kinds of speed-up ratios are provisional rather than permanent, since classical computing methods keep improving too, and a result that looks decisive one year can shrink considerably the next as classical algorithms get optimized specifically to compete with the quantum claim that inspired the comparison in the first place. This is not a new lesson quantum researchers just learned. It is a hard-earned one. Years ago, there was genuine excitement that a specific quantum computing approach called quantum annealing might deliver dramatic speed-ups for machine learning training tasks specifically, generating its own wave of confident predictions at the time. That early optimism largely did not translate into clear, durable practical advantages once researchers dug deeper. Many proposed quantum speedups for AI-adjacent tasks have historically shrunk or vanished entirely once classical methods were properly tuned and optimized to compete on equal footing. That history is exactly why the most credible, technically serious voices in this field have increasingly focused their most confident claims specifically on physics simulation and chemistry, areas where the theoretical case for quantum advantage is considerably firmer, rather than on general artificial intelligence training and inference, where the case remains genuinely murky and heavily contested, even among experts who are otherwise bullish on quantum computing's long-term potential. If you're finding this breakdown useful, go ahead and hit that subscribe button because we cover stories exactly like this every single week, connecting the dots most channels leave scattered. Now here is where this story takes a genuinely revealing turn, because the reaction from the company you would expect to be most threatened by these claims tells you almost everything you need to know about how seriously the AI chip industry actually takes the obsolescence narrative. NVIDIA, the company that would supposedly become worthless overnight if quantum computers truly made every GPU obsolete, has spent the past year aggressively investing in and building infrastructure specifically designed to integrate quantum computing directly alongside its own GPU-based systems, rather than treating quantum hardware as an existential threat to be dismissed or ignored. At its GTC developer conference in March of 2026, NVIDIA CEO Jensen Huang made the company's position unmistakably clear, describing quantum computing as an important part of the next generation of computing ecosystems and platforms, explicitly positioning it as complementary infrastructure rather than a rival technology racing to replace GPUs entirely. NVIDIA introduced something called NVQ-Link, an open architecture specifically designed to integrate quantum processors of essentially any type with GPU-powered AI supercomputing infrastructure, alongside a dedicated, accelerated quantum computing research center built around the company's own high-end GB200 hardware. If NVIDIA genuinely believed quantum computers were about to render its entire product line obsolete, this would be a spectacularly strange, self-defeating way to respond to that threat. The actual technical reality, once you dig past the sensational headlines, looks considerably more like partnership than replacement, and understanding why requires appreciating what each type of hardware is actually good at. Quantum processors excel at very specific, narrow categories of computation, certain kinds of optimization problems, sampling from complex probability distributions, and simulating inherently quantum mechanical physical systems. GPUs excel at the kind of massively parallel, repetitive numerical computation that dominates modern artificial intelligence, training neural networks through millions of repeated matrix multiplications, running inference across enormous language models, rendering graphics and countless other tasks that have essentially nothing to do with quantum mechanics at all. Even in hybrid workflows where quantum processors handle a genuinely useful role, they typically handle only a narrow, computationally difficult slice of a larger problem, while classical GPUs handle everything else, the actual model, training, the inference, the deployment, and the vast majority of the surrounding computational workload. There is also a fascinating twist buried inside this entire conversation that rarely makes it into breathless headlines: quantum-inspired algorithms running entirely on classical GPU hardware, with zero actual quantum processors involved anywhere in the pipeline. Researchers have developed mathematical techniques originally inspired by quantum computing principles, things like quantum-inspired principal component analysis and quantum alternating operator ansatz methods for optimization, that run perfectly well on ordinary currently available GPU hardware, delivering meaningful speedups of up to 100 times over traditional CPU-based implementations for specific categories of problems like portfolio optimization and hyperparameter tuning. In other words, some of quantum computing's most practically useful contributions to artificial intelligence right now are not coming from actual quantum hardware at all, but from quantum-inspired mathematical thinking that classical GPUs can already execute today, no exotic refrigerated quantum chip required whatsoever. It is worth pausing here to walk through exactly why translating AI workloads onto quantum hardware is so much harder than swapping one chip for another, because the underlying technical mismatch explains almost everything about why this obsolescence narrative struggles to hold up under real scrutiny. Getting classical data into a quantum computer in the first place requires a process called quantum encoding, essentially translating ordinary numbers into quantum states a processor can actually work with. For small, carefully chosen data sets, that encoding step is manageable. For the kind of massive, high-dimensional training data that modern AI systems consume by the billions or trillions of data points, encoding overhead alone can completely erase whatever theoretical speedup the quantum computation itself might have offered, before the actual calculation even begins. Researchers studying this specific bottleneck have identified data encoding overhead as one of the dominant, unresolved barriers standing between today's quantum hardware and any kind of broad, practical takeover of mainstream AI workloads, right alongside noise from imperfect qubits, latency in moving information between quantum and classical systems, and a general mismatch between the software tooling AI engineers already know how to use and the specialized programming quantum systems currently require. There is a useful historical parallel worth drawing here, because the technology industry has seen this exact pattern of overheated claims, followed by a more grounded reality before, and remembering that pattern helps calibrate expectations properly. When GPUs themselves first started being repurposed for general computing tasks beyond graphics rendering in the mid-2000s, some early coverage predicted they would immediately and completely replace traditional CPUs across the entire computing industry within just a few years. That obviously did not happen in the way the most dramatic predictions imagined. Instead, GPUs found their genuine, durable niche, specifically the massively parallel numerical workloads they excel at, while CPUs remained essential for the sequential, general-purpose tasks they were always better suited to handle. Decades later, that same complementary relationship still defines how modern computers are actually built, CPUs and GPUs working together, each handling what it does best, rather than one technology wholly replacing the other. Quantum computing appears to be tracing a broadly similar trajectory relative to GPUs today, finding its own genuine specialized niche rather than fulfilling the more dramatic full replacement narrative that tends to generate the most attention-grabbing headlines. McKinsey's own 2025 industry analysis, frequently cited by companies genuinely bullish on quantum AI convergence, actually reinforces this more measured hybrid framing rather than supporting a full obsolescence narrative. That analysis specifically identifies quantum computing as addressing certain core constraints within artificial intelligence infrastructure, algorithmic efficiency, limitations, memory bottlenecks, and specific compute-heavy bottlenecks, while explicitly framing quantum processors as eventually joining GPUs and specialized AI chips called TPUs inside AI data centers, handling specialized workloads like optimization and sampling, rather than wholesale replacing the general-purpose computing infrastructure that currently powers essentially the entire AI industry. Joining is a fundamentally different claim than replacing, and that distinction matters enormously for understanding where this technology genuinely stands right now. There is also a deeper, more fundamental technical barrier worth understanding, one that explains why quantum computers remain poorly suited to replacing GPUs for most current AI workloads, even in a hypothetical future, where quantum hardware becomes dramatically more powerful and reliable than it is today. Modern artificial intelligence models are built from staggering numbers of parameters, weights, and biases, numbering in the hundreds of billions or even trillions for today's largest language models, requiring enormous amounts of classical data storage and classical numerical precision to train and run effectively. Quantum computers fundamentally operate on qubits, which represent information in a completely different probabilistic way, and translating this specific kind of massive, dense, classical numerical computation that dominates AI training into a form quantum hardware can efficiently process remains a genuinely unsolved, actively researched problem. Not a solved engineering detail simply waiting for bigger, more reliable quantum chips to arrive. Researchers working specifically on quantum machine learning have been explicit that, as of right now, in 2026, meaningfully integrating quantum processing into embedded and edge AI systems remains technically feasible only in narrow, highly experimental configurations. Hybrid workflows where classical hardware handles the bulk of sensing and processing while offloading only a very narrowly scoped quantum subroutine to a separate quantum processor, not the wholesale quantum takeover of AI computation, the more sensational headlines tend to imply. None of this means quantum computing has no real meaningful role to play in the future of artificial intelligence, and it would be its own kind of oversimplification to swing too far in the opposite direction and dismiss this entire field as pure hype with zero substance behind it. Specific, narrow applications genuinely do show real, credible promise. Quantum-enhanced approaches to predicting chaotic, unpredictable physical systems, the kind of turbulent, hard-to-model behavior that shows up in weather patterns, fluid dynamics, and complex financial markets, have shown genuinely measurable improvements when combined with classical artificial intelligence forecasting techniques in recent peer-reviewed research. Quantum processors also show real promise for specific optimization problems, portfolio construction, complex supply chain routing, and drug discovery-style molecular simulation, exactly the kind of narrow, well-defined, quantum mechanically relevant computational tasks, where quantum hardware's fundamentally different approach to representing information offers a genuine, defensible theoretical advantage over classical computing methods. So let's return to that original headline claim and actually deliver a real, honest verdict, rather than either uncritically amplifying the hype or dismissively waving the entire field away. Did quantum computers just make every AI chip in the world obsolete? No, and the proof of that lies precisely in how the AI chip industry itself is actually responding to these developments. NVIDIA is not laying off engineers or panicking about its GPU business becoming worthless. It is actively building infrastructure, specifically designed to integrate quantum processors as complementary accelerators working alongside its existing GPU-dominated ecosystem. treating this moment as a genuine expansion of accelerated computing's overall toolkit rather than an existential threat demanding a defensive pivot away from the hardware that built the company's entire market position in the first place. What is actually happening underneath all the sensationalized headlines and inflated speed-up ratios is a genuinely interesting, considerably more nuanced story about specialization rather than replacement. Quantum processors are gradually finding a real, defensible role handling specific, narrow categories of computation that classical GPUs genuinely struggle with. Certain optimization problems, certain kinds of physics and chemistry simulation, certain sampling tasks tied to inherently quantum mechanical systems. GPUs, meanwhile, remain and will very likely continue to remain for the foreseeable future, the dominant essential workhorse behind the vast majority of artificial intelligence training and inference happening around the world today, precisely because the fundamental mathematical structure of modern AI models maps so naturally onto the kind of massively parallel classical computation GPUs were specifically engineered to excel at. There's also a straightforward economic angle worth including here, because chip obsolescence claims tend to ignore just how much existing infrastructure investment currently anchors the entire AI industry to GPU-based computing. Major cloud providers and AI companies have collectively poured hundreds of billions of dollars into building GPU data centers over the past several years, infrastructure that remains fully functional, actively generating revenue, and nowhere close to being written off as a sunk cost. Even in a hypothetical future where quantum processors genuinely do become dramatically more capable and reliable than they are today, the practical financial reality of replacing that enormous existing GPU investment would unfold over many years, not overnight, regardless of how impressive any individual quantum benchmark result might look in isolation. Technology transitions of this scale, ripping out and replacing the fundamental computing infrastructure an entire global industry depends on, simply do not happen at the pace dramatic headlines sometimes imply, even when the underlying technical case for eventually making that transition is genuinely sound. It is also worth directly addressing why claims like this Chinese optical chip announcement tend to spread so quickly and so widely despite the underlying uncertainty, because understanding that dynamic helps build better resistance to it going forward. Speed-up numbers are inherently easy to sensationalize and hard for casual readers to properly contextualize. A headline reading 1,000 times faster carries enormous visceral impact, regardless of whether that specific ratio applies to a narrow, favorably chosen benchmark task or to the broad, general-purpose computing workloads that actually determine real-world usefulness. Serious technology journalism increasingly tries to include the necessary caveats: unresolved manufacturing issues, narrow benchmark scope, lack of independent verification, but those caveats rarely travel as far or as fast as the initial, more dramatic headline number itself. Once a story starts circulating widely across social media and aggregator sites, competing for attention and clicks. The genuinely exciting, credible version of this story is not that quantum computers are secretly, single-handedly replacing your GPU infrastructure any minute now. It is that two fundamentally different complementary computing paradigms are gradually learning to work together, each handling the specific category of problem it is naturally best suited for, gradually expanding what is computationally possible across science, medicine, logistics, and yes, eventually, certain specialized corners of artificial intelligence as well. That is a genuinely compelling technology story on its own merits. It simply happens to be a considerably less dramatic, less clickable headline than every AI chip in the world just became obsolete, even though it is the version of this story that actually holds up once you look past the initial claim and into the evidence sitting directly underneath it. If you want to keep following where this genuinely fascinating story goes next, make sure you like this video and subscribe so you don't miss the follow-up, because between NVIDIA's own quantum investments, the ongoing chase for verifiable quantum advantage, and results like this Chinese optical chip claim still awaiting real independent scrutiny, this particular corner of the tech world is moving fast enough that the next major headline is probably closer than most people currently expect.